It has happened countless number of times in the past, and it will happen again countless number of times in the future. A large space rock floating out in space will be nudged from its current orbit, setting it on a collision course with the Earth. That is, unless humans, the most advanced species the Earth has ever produced, do something about it. I'm your professor, Glenn Torres-Spelliscy, and this is the Space Law and Policy podcast series. Thanks for joining me. Perhaps the most famous of the space rocks to do catastrophic damage here on Earth was the Chicxulub impactor. Now, we don't know a lot of specific details about the Chicxulub impactor, but it was big. It was between 10 and 80 kilometers in diameter and weighed between 1 trillion and 100,000 trillion kilograms. The size of a mountain and moving at 20 kilometers per second, it slammed into Earth near what is now the Yucatan Peninsula during the springtime. The impact left a crater 150 kilometers wide and 20 kilometers deep. It released as much energy as 100 teratons of TNT, more than 1 billion times more powerful than the bombs dropped on Hiroshima and Nagasaki. The results on the living organisms of Earth were devastating. Powerful earthquakes and tsunamis pummeled the North American continent. Enormous wildfires erupted even thousands of miles from the site of the impact, and poisonous clouds and rocks rained down on the Earth, acidifying oceans and killing marine life. The impact generated significant climate impacts that would collapse food webs and send numerous species spiraling towards extinction, the most famous of which were, of course, the dinosaurs. In the end, nearly 75% of all living organisms went extinct in the aftermath of the strike, an event known as the KT mass extinction. Those land-based dinosaurs have been dominating the surface of the Earth for 165 million years. But comparatively, the human evolutionary tree split from our great ape ancestors to form the Homo genus approximately 2.5 million years ago. The human age, even dating back to the earliest members, is just a small blip on the history of life on Earth. What this all demonstrates is that even animals that are so well adapted to life on Earth that they can survive as the dominant group for 165 million years can be erased in an instant by a rock floating through space. Importantly, though, it doesn't have to be a big rock like Chicxulub to cause significant damage. Sure, a mass extinction level event isn't going to come along because of a small rock, but those small rocks could still devastate significant areas of the Earth. And if they hit a major urban area, they could result in significant loss of life. In 2013, a small asteroid, approximately 20 meters in diameter, exploded in the sky over Chelyabinsk, Russia, causing millions of dollars of damage and thousands of injuries. If it had impacted the Earth, the devastation would have been worse. In August of 2022, asteroid 2022 PF, approximately 45 meters across, zoomed past the Earth at an astronomically too close for comfort distance of approximately 1.7 million kilometers. In November 2022 RM4, an asteroid with an estimated diameter of 330 to 740 meters, just smaller than the largest building in the world, which is Dubai's 2,700 foot tall Burj Khalifa, passed within 1.5 million kilometers of the Earth at around 84,000 kilometers per hour, nearly 70 times the speed of sound. If one of these asteroids, just a fraction of the size of Chicxulub, were to impact the surface, it would hit with the force of 30,000 megatons of TNT. The result would be a 6.2-mile impact crater nearly 2,000 feet deep. A major earthquake would rock the area with a 60-mile radius, causing further structural damage. Radiation would quickly spread over a large area, and in the end, a rock that size would produce an explosion about twice as powerful as the bomb that was dropped on Hiroshima. If such an asteroid hit a populated urban area like New York City, millions of people would immediately be incinerated, and millions more would die from radiation poisoning in the week that followed. Even smaller asteroids and comets could be devastating if they impact a particularly vulnerable area. Now, how likely is an asteroid big enough to destroy a city to hit in the near future? Well, the odds are very small. NASA estimates them to be somewhere around 0.1% per year. And even if one does come toward the Earth, the odds suggest that it would land in water, which could cause some issues for coastal cities, but would not be as devastating as a direct land impact. Indeed, the odds of a 10 plus kilometer wide asteroid like Chicxulub hitting the Earth are almost negligible, at 0.0000001%. Now I know those sound like good odds, but when we expand the time period over billions of years, and after all the Earth is approximately 4.5 billion years old and is expected to survive for another 8 billion years, the likelihood of an asteroid impact of that size becomes a near certainty. Indeed, scientists estimate that an asteroid the size of Chicxulub impacts the Earth approximately once every 250 million years. That's nearly 20 such impacts over Earth's history. The rate of frequency for much smaller objects is of course higher. According to NASA, every day Earth is bombarded with more than 100 tons of dust and sand-sized particles. About once a year, an automobile-sized asteroid hits the Earth's atmosphere, creating an impressive fireball, and burns up before reaching the surface. Every 2,000 years or so, a meteoroid the size of a football field hits the Earth and causes significant damage to the area. And while these estimates are sobering, they don't provide a lot of policy guidance for those of us on Earth looking to avoid such a fate. After all, we don't need to know if an asteroid is likely to strike in the next 250 million years. We need to know if an impact is likely tomorrow. So the first step to avoid destruction via space rock is to determine where all the space rocks that could possibly threaten Earth are. That's no easy task. The problem is there are a lot of each category. There are an estimated 1 million asteroids in our solar system. There are about 4,000 known comets with trillions likely in the faraway Oort cloud, and an innumerable amount of meteoroids. The good news is that we don't have to be concerned with every possible impact. Most meteoroids, for example, are so small that they simply burn up in the Earth's atmosphere, with nary a blip. But most of the dangerous objects, well, they won't approach Earth either in the foreseeable future, and therefore pose no immediate threat. There are a number of these objects, however, that do approach close in astronomical terms, and these are known as near-Earth objects, or NEOs. So when we are talking about developing space awareness, one of the things that we have to know is the position and the trajectory of these NEOs. In 2005, NASA was tasked with discovering all physical objects larger than 140 meters, or 0.14 kilometers in size, by Section 321 of the NASA Authorization Act of 2005. The act called for NASA to have completed the survey by 2020. It did not. Although it did identify most of the largest asteroids, including approximately 90% of all objects larger than 0.9 kilometers in diameter, we've only identified about 30% of those objects greater than 0.14 kilometers in diameter. As NASA notes, at our current pace, we will discover less than half of all 140-meter objects by 2033. How can we do better? Well, one way would be to improve the way that we detect asteroids and comets. Although we have Earth-based telescopes and radar capabilities, most analysts agree that a space-based telescope would provide significant benefits, particularly with respect to the detection of smaller objects. In 2019, after years of preparation, the NEO Surveyor program was initiated. NEO Surveyor is a new infrared space telescope designed to give us eyes in the sky. It will improve our overall detection capabilities significantly, and is set to launch sometime between 2026 and 2028. And if the first issue is finding asteroids that could potentially cause deadly impacts, then the second issue must be finding a way to avoid those collisions. After all, what good is knowing that a Chicxulub impactor is coming if we can't change our fate? And changing our fate has been something we've been focused on over the last years. In 2022, NASA demonstrated the capacity for the first time to potentially alter the orbit of an asteroid that is headed toward impact with the Earth. A small spacecraft called DART, which stands for the Double Asteroid Redirection Test, was launched with a simple purpose: crash into an asteroid to see if the kinetic impact altered the asteroid's course. The target was a double asteroid system traveling through our solar system that was not on an impact path with Earth. The larger asteroid was Didymos, and the smaller asteroid was Dimorphos. Even the smaller asteroid was about the size of a football stadium, with the larger asteroid being about 5 times that size. So neither of these were small. DART's target was the smaller orbiting asteroid, and on September 26, 2022, DART made impact, moving at over 6.1 kilometers per second, and indeed it did change the orbit of the asteroid dramatically. And that's a remarkable feat. We sent a small spaceship millions of miles away and crashed it into a rock, dramatically altering its orbit. This was clearly just a test, but it demonstrated a capability to potentially defend the Earth should the need arise. And there are also other potential options for asteroid deflection discussed in the lecture book, and this is critical because one method might work on one type of asteroid, but not another that has a different composition. Many of these methods are likely to be tested over the coming decade. Indeed, humanity's ultimate existence may be determined by the success of these tests and our demonstrated ability to successfully defend the planet from these incoming threats. Well, that does it for this week's podcast. Tune in next week for another edition of the Space Law and Policy podcast series. Thanks for joining me.